All right, so today we're going to be talking about a few different scenarios involving ropes, cable, string. Essentially, we're talking about tension in kind of three different ways. So the first way is just how do I calculate the tension on a string or on a rope cable? So let's say that I have a rope and I suspend a 10 kilogram mass from it. It's up in the air. So let's start with what we know. We know that there is a force of gravity pulling that mass down. Okay, or it's exerting a downward force on the object. That object then pulls down on the rope. And I'm going to guess they're going to pull down the same amount. So in this case, the force of tension, F of t, will be equal to the force of gravity. And then, of course, we'd have, with this pulling on the string pulls back kind of against the mass there. Newton's third law, every force is an equal but opposite force. The big thing though is, so assuming this thing isn't moving, it's just suspended there, it's just hanging. Um, I can find that force of tension really easy. The force of tension, which we said is equal to the force of gravity, is just equal to mass times the acceleration due to gravity. So in this case, that tension is going to be 10 kilograms times negative 9.81 meters per second squared. Just have to move the decimal over. I should get negative 98.1 newtons. All right, that's my force of tension here. Just hanging there. And then the thing about tension, so what tension is essentially it's the force that's transmitted throughout a rope. So that whole mass there, that gets transmitted throughout the entire rope. And then eventually what we would find, like let's say it's hanging off of like an eye bolt there. That's how much force that rope would be exerting kind of on whatever's attaching it to the ceiling there. All right, so that's just how we calculate tension if the thing's not moving. But let's say, I'm going to scroll down. Let's say in this case, we have that same mass, 10 kilogram, and this time it's attached to a bar, a pulley, anything like that. But in this case, that bar or pulley is being accelerated upwards at 1 meters per second squared. Now, my force of tension isn't just the mass, the force of gravity from this, because, kg, because I still have F of g pulling down, but in this case on the rope, so then that F of g is pulling down on the rope. But I also have, this thing is moving now. It has a net force. The net force is going upwards because it's being accelerated upwards. And that deals with Newton's second law of motion, is that the net acceleration of or net force for an object must be in the same direction as the acceleration. So if this whole thing is being lifted up this way, it's lifting up, it's pulling on the string, which is pulling on the mass, and the whole thing's accelerating upwards. So in this case, my force of tension, the whole force on this string, is equal to the force of gravity plus that net force. And that kind of makes sense. Like if I pull on it, that string is going to experience a lot more force. In fact, if this thing was near breaking and I pull on it too fast, it's going to snap the string. So force of gravity is still just equal to mass times gravity. But now for net force, I'm going back to that kind of original equation we have, which is just mass times acceleration. So in this case, we have 10 kilograms times gravity, which is negative 9.81 meters per second squared. And I have to add the mass again, 10 kilograms, times the acceleration of 1 meter per second squared. All right, so let's go, this we know from before is negative 98.1 newtons plus, let's even get rid of the sign here isn't going to, the sign here is not that important. is what I'm trying to say. Because essentially, it doesn't matter that these things are pulling in opposite directions. That actually means there's more tension on the string, okay? So ignore signs here. So I'll even make that positive. 10 times 1 is still 10 newtons. So the total tension on this rope is 108.1 newtons. So the total, the net force plus the force of gravity, that tension is equal to 108.1 newtons. All right. So another way to look at it, so let's come up to this guy. We're going to work with this top one here. Let's say though, and we'll go down for it. So that 10 kilograms. Before I figured out one rope, the force of tension we said was 98.1 newtons. Let's say rather than having one rope suspending it, we have, let's draw the bar there. Let's say we loop that rope around the bar and attach it there. I now have two strings, two ropes, two different segments of rope here. In this case, the force of tension on each segment is going to be half what it would be, with just one cable there. All right. So if I grab my calculator here, 98.1 divided by 2, probably could have done that in my head, for 9.05. All right, so that's my phone. Hit that. All right, last thing I need to talk about. Let's say that I have, you know what? I have a 10 kilogram sled here. It's on a frictionless surface is what I'm going to say. On that sled, I have two people pulling on it. And they're pulling on a rope. So let's say I want to know what the acceleration of the rope will be. And we're going to say each person is pulling on the rope with 10 newtons of force. And if I consider like there's a horizontal here, each one is pulling at 30 degrees away from the horizontal. All right. I want to know the main force. Really what I'm looking for is the net force. Well, to figure that out, I need to figure out, we can even call this the x direction if you want. I need to take both of these triangles here. So that's 10 newtons, and then I have, that's 10 newtons. I need to know, okay, so I've taken both of those ropes, okay, 10 newtons on each of them. They're both 30 degrees from the horizontal, right? I have an f of x there, and I have a force in the x direction there. I need to solve for f of x here. And the way that I'm going to do this is I'm just going to use my trig properties, my SOHCAHTOA. So to find f of x is adjacent to the angle I have, so it's going to be the hypotenuse. Adjacent would be CAH, C-A-H, so I'm going to use cosine of 30. Down here, it's going to be the same thing. All right, so let's go back to the calculator. 10 times, oh, no, let's start over. Let's go 30 cosine times 10. All right, so each of these will have a force in the x direction of, let's go with 8.7, 8.7. Together, my net force, so a total net force, when I add these in the x direction, add those together, I should get 17.4 newtons. All right, and now I know the mass, and that's equal to mass times acceleration. So 17.4 newtons is equal to 10 kilograms times A. A is what I'm looking for. Divide both sides by 10 kilograms. All right, so now back to the calculator. 17.4 divided by 10. 1.74 is the acceleration here. Meters per second squared. Essentially, it just comes down to trig. Using those angles, the big thing is just that we're breaking things down into movement into the x direction, movement in the y, just like we did with slopes. In this case, we have two triangles. We need to figure out which direction both of them are going in the x direction. This you will see when it comes for like hauling um, or towing things, pulling things out of ditches. Uh, Sometimes even like dog sleds work this way, stuff like that. I hope that helped. I hope this stuff was pretty basic, even though it was kind of varied with all that stuff. So with that, good luck.